The question is, uh, 1 minute. Yeah. Let 0 less than alpha less than 1 be a real number.
Hmm.
The number of differentiable function y such that
Hmm.
such that means 0 to matlab the function y goes to 0 to 1 to 0 to infinity.
Closed or open?
Close 0 to 1
Hmm.
goes to close 0 open infinity.
Okay.
Having continuous derivative on 0 comma 1 closed.
Closed.
0 open
Okay.
and satisfying y dash t equal to y of t to the power alpha whole whole yt whole to the power alpha, where t belongs to closed interval 0 to 1
Hmm.
and y0 equal to 0. इसका ऑप्शन है कि कितने एग्जैक्टली वन, एग्जैक्टली टू, फाइनाइट बट मोर देन टू इनफाइनाइट, मतलब नंबर ऑफ डिफरेंशियल फंक्शन.
Okay, then fine. Let's think. So 0 is there, that's a trivial solution. So can you say the options once? I think.
Option is 1, 2, or exactly sorry, finite but more than 2 or the infinite.
Okay. I want to say that there is a unique solution. Okay. I want to say that there is a unique solution uh, because this is a first order differential equation and initial condition is given. So there should be a unique solution. but how do I say that? So there is a theorem called Picard's theorem or Piano's theorem, one of them. So, but basically what I want to say is the following. Y prime t equal to f of yt comma t. Okay, this thing, if y x naught equal is given, okay, which is this is the initial condition, so maybe t naught, okay, where f is just a function, f is a function of two variables, okay. This, so this setup, is this setup clear? This is an initial value and y satisfy y prime and the initial t, they satisfy this relation where f is some function. Like for example, what is f in our case? In our case, f of, I will say u comma v is u to the alpha, correct? In our case, that is what f is, okay? So Picard's theorem says that under this condition, and so that example I will remove. Under this condition with this initial value and the condition that f is Lipschitz continuous, yeah, implies there is a unique solution. And but let me first check this if this is correct. And I've been also inclined to think that maybe some heuristic would also answer the question without quoting this theorem. This is a first theorem in differential equations course or study differential equations. But let me think for a minute if there is some other, just from heuristics. Because you cannot solve this kind of equation, that's out of the picture. You cannot solve, you cannot find a closed formula for this kind of thing without using this kind of uniqueness result. It's not possible to find a closed formula because you know that. So I mean, you don't expect to have a closed formula, at least that you know. So that's out of the picture. Now, if you want some heuristic, means some explanation as to why the solution is unique. Where is the color? Yeah. Oh, the color is black, so it's not visible. Okay. Okay. Right. Sorry. So heuristic. Yeah. So if the point is that if this equation is given and this starting value is given, then why does that imply that the solution is unique? Let's think. Well, you know that given this condition, you know the derivative at 0 is also given. In this case, it is 0, right? So it tells you what the slope of the graph means. Whatever the function be, let's say you don't know that, but you know the slope, right? You know the slope, and so I mean, that tells you the function in a neighborhood up to, up to any degree of accuracy you want. That tells you the function in a neighborhood, I suppose. Agree with that. And when you go to that point, then again, you know the slope, right? And that kind of intuitively tells you that you sort of know the function. But that's a heuristic. If you want to make it rigorous, you get this theorem. That's the point. I mean, I can discuss the proof of this theorem, but if you want to. So, but now, that's the first step. Second step is let's check if the theorem is, if I stated it correctly. That's always a chance because I don't use it very often. So I can forget. So let's see. Maybe we should just check it online. I mean, there is, I have the book, but it's downstairs. Simon's differential equations book is there. It's there, but yeah, okay. So Picard's theorem. So let's, yeah, now Picard's theorem, of course, is a big, there are a lot of Picard's theorems, but we want for differential equations. Okay. We don't want examples, we just okay, so it's Picard Lindelof. I did not know Lindelof was so there. So yeah, read here. Study specifically the study of differential equations. The Picard-Lindelof theorem gives a set of conditions under which an initial value problem has a unique solution. It is also known as Picard's existence theorem, Cauchy-Lipschitz theorem. Okay, why it's called like that you can understand from the Lipschitz condition, or the existence and uniqueness theorem. And these are the people who have. Yeah, let's try to understand the statement. The proof is very interesting. It's based on this Banach fixed point theorem, which is very simple. It's a very simple fixed point theorem. Very beautiful, but let's come one step. Yeah. So D is a closed rectangle in this. So you can just imagine that D is in R2. Okay. That so you can just imagine that. Sorry. Yeah. Just a closed rectangle. Okay. Just a closed rectangle. And the reason why it is Rn, it's fine, but you can just take n to be 1. Our situation, that suffices. So you can imagine a rectangle, take a point in the interior of the rectangle, and d be the function, f is the function. Oh, yeah, f was the function, the two variable function. Be a function that is continuous and Lipschitz in y. Okay, so you want Lipschitz only in one variable. I said Lipschitz in both variables, but you want Lipschitz in only this variable. Then there exists an epsilon such that this initial value problem has a unique solution on this interval. Right. So yeah. So the statement I have stated correctly only. So let me now tell you how to parse it from there. I mean, if you understand it from there. So what did they say? They said take a closed rectangle. Okay, so take a closed rectangle. This point is what they are saying to take a point. So you take the point P. Okay, and this was the initial value. Only that their notations are different. So they are using it in the other way, but it doesn't matter. This. So with this condition and this condition, yeah, so this F was Lipschitz continuous. We get a unique solution, but the condition was that in a neighborhood there is an epsilon such that in this neighborhood, so this is the neighborhood. Okay, this is the neighborhood in which you get a unique solution. And in our case, that will mean that in 0 to epsilon, there is a unique function. Okay, there is a unique solution. But then it will imply that there is unique throughout. Okay, but I'm not getting into that. There is some other arguments needed, cover and maximal neighborhood and so on. So you can imagine, because it's a connected interval, there will be a unique solution throughout. Right. So that is what it is. And you know what is Lipschitz continuous? I mean, I should have asked that. If you don't know, you
Actually, I
should.
don't.
You don't know
No.
yeah, then you should know. Then you should see the definition of this. So check the definition of Lipschitz continuous and prove that x going to x to the power alpha is Lipschitz. Okay. So that being said, maybe I should just tell you some things here. So there is a notion of continuity, right? And then there is a notion of uniform continuity. So you can take this as homework. And then there is a notion of Lipschitz continuity. Right. Lipschitz continuous. And then in that, there is a notion of continuous plus bounded derivative. Yeah, so maybe if I don't tell you what this is, then I should not. So Lipschitz means that there is a alpha such that this happens. In the simplest case, that's what it means. Okay. And so bounded derivative implies it's Lipschitz. This is Lipschitz. Okay. Yes, some alpha for this. And this is inside C1, which is C1 is continuous derivative, which is the initial condition. Okay. So this is continuous. If the derivative is continuous, yeah, it really depends. So continuous derivative. So when you say C1, you don't, yeah, so my definition is fine. According to this, yeah. So continuous derivative, so by C1, I mean, again, this is a standard term. So if I say, so let me say that C1 on closed 0, 1, this means continuous and derivative exists on open. We usually don't ask the derivative to exist on the closed and continuous. Okay. Yeah. I think this is how it is. Okay. Right. So you should now, so what the work you should be doing is try to, not try to, this is the homework, that you should look at this theorem, read this, try to, you understand this theorem, try to read the proof. Okay. And maybe this Sunday, one of you can present the proof with some example is there, that it's fine. And there is a detailed proof. Yeah, all these things are there. Wait a minute. So this is there, but I wanted to also say, look at this Lipschitz continuous, because there are other related notions like alpha continuity. And if you don't know those things, then you have to know. So, and the absolute continuity, yeah, this alpha holder continuity. Yes, as I was telling you, right, that continuously differentiable sits inside this. And you see the significance of this result is that it is used in the Picard-Lindelof theorem. That's the significance of this condition. But let's organize things. So 1 minute. Yeah, so I just need to look at whether they ask for it to be on closed or not. That definition. No, they don't have a dedicated page. So C1 function, whether continuous first derivative, but they really don't say if it should be continuous on closed. The derivative should exist on closed or open. Usually we do not ask for closed. You see, so no. Yeah, so it's on all of okay. There is a problem. I will wait. So let me. If that is the definition, then there is a problem. Yeah, just a minute. Because there is no clear. Well, yeah, I think that is wrong. I think. Yeah. Let's just look at it in some book. I think. So you see where the problem is. I am asking if the definition of C1, the differentiability should be on open 0, comma 1, or it should be imposed on closed 0, comma 1. Okay, and if it is imposed then on closed 0, comma 1, then it is not good. Then there is some problem. So just look for C1. Do you find C1 anywhere? Maybe they don't have that notation. Right, it is here, I think, 219. Let's see what is there. That's a minor thing, but it's good to clear it. So look for a definition. Yeah, on open set it is a different game, but on closed set the definition is not very clear. It's on open set it is quite clear what the definition should be. Okay, wait. That is not very clear to me. Let's see. Or yeah, smoothness is correct. But then smoothness will be defined on closed interval, on open intervals. 1 minute. Yeah, they do it everything on open, then there is no problem. Okay. Yeah, let's try to resolve it. Okay. So here is the so I've told you to read the Picard-Lindelof theorem, but now let us try to formulate a proper definition of C1 0 comma 1. Okay, right? So certainly we want continuity on close 0 comma 1. Okay, differentiability on open 0 comma 1, and we want this, and f dashed is continuous on this. But the question is, should we put in the definition that its derivative exists on the endpoints also? Because then it would be one-sided derivative. And oh, wait. Yeah, so if you take this as the definition of C1, okay, then no, wait. So let's see. This as the definition of C1. Do you think this is good, or should we want the continuity at the endpoints also? Or the derivative to exist on the endpoints also? So with this, what happens is this does not imply that the derivative is bounded. Okay, so C1, right? This does not imply, if you take this definition, that f dashed is bounded. Can you give an example? Where the derivative is continuous, but it's not bounded on to be something.
You can take 1 by x.
But 1 by x, so you want to take f as 1 by x?
Yeah.
No, but that doesn't make sense. It won't be continuous on close 0 comma 1, right?
Okay.
That's the twist, right? So you have to. No, but right, yeah, it won't be continuous. Any idea? So if I take a continuous function, antiderivative of x, yeah, I think. So we want a function which is nice. It's a continuous function on close 0 comma 1, differentiable on open 0 comma 1, but the f dashed is not continuous. Yeah. I think this will not happen. Yeah, I think this will not happen. So you will want to show that f dash is bounded. Yeah, I have resolved one thing. So let me tell you that here you take on close 0, 1. Okay. Okay. And then so this is correct. It exists and it is bounded. Yeah, this is not the best way to say. I'm not able to say it, but please do this homework. What is the homework here? It is to show that everything is, there, but that's the only interesting thing to do. To show that each of the inclusions is not X. You have to find counter examples for every part. Okay. And here everything is on close 0, 1. Or, here there is no counter example, of course. So, yeah. This is, of course, equal that you know. Right? This is equal. Okay. Obviously, there is a more elaborate exercise on Wikipedia about absolute continuity and so on, but it's fine. You do this one for now, and then please return it to me. Okay. Tell me. Last day also I gave some homework, so you should do it. Sure. So this is something to do. Okay. Then you can really understand what the condition is trying to say. Okay. Now this is a different problem. Okay. Here we are saying that, okay, if you, so maybe I will not say this anymore, otherwise it will be a confusion. So I'm just saying continuity on this and so on and like this and this. So now does it imply f dash is bounded? So maybe that. Is it clear, the question? Is f dash bounded? So here I'm not putting the endpoints. If I put the endpoint, then of course it's bounded because it's a continuous function on closed interval, extreme value theorem. Here will it be bounded? Because if I think about 1 by x, right, then if I take f dash to be 1 by x, I take fx as log x. It also has the same problem that you cannot extend it on the close 0, 1. Look, the derivative may not exist on the boundary. That is clear, I suppose. Right? You take this kind of function and no, sorry, nothing, nothing. That's bad. Yeah, so this will also be a homework if we cannot resolve it right now within the 2 minutes. Fortunately. So it's continuous and Yeah, this is possible. Okay, this is possible, and that it is not bounded. I think you take root x, right? Correct? Yeah, so this will be homework. Answer is no. And this will actually related to the previous homework also. Yeah. That is the, yeah. Okay, so this is the second homework. So you should learn these things and then you read the Picard, you read that and the three things. Don't have to read the proof, but try to understand the statement and see the examples. Okay. Siemens, so GF Siemens is an engineering, no, not GF, I don't know which Siemens, but just Siemens Ordinary Differential Equations book you can consult. It's a basic, very, very simple book. It's followed by in IIT also, BTech students. So, but it's very nice. Still, it's a very nice book. It doesn't create too many problems. Very nice book. Ordinary Differential Equations. You should read this portion from there. It's very, very nice. Get a lot of intuition from physics and so on. So you should look at it. Then let's meet after 10 minutes and yeah, okay, or 8 minutes whenever this restarts. Okay. See if you have any questions.